So let's see. So our this is what our announcements are today. So we have pump set due today, and pump set 5 is coming. Okay. In fact, I think it's posted.
It is.
And we have our makeup tomorrow from 9 to 10 in room 2540. And we have problem session, so you're going to have a lot of me. Wow, those of you who care. All right. Nate's going to totally throw me off sitting in the back there, but I'll survive. All right. So, we've talked about the nature of entanglement. What I want to talk about for the next couple of lectures is the generation of entanglement. All right, so the question is, what's necessary to create an entangled state? So we think about if our Hamiltonian is separable. So let's imagine we have a bipartite system. So we have a Hilbert space for the two subsystems, degrees of freedom. And my Hamiltonian, if it's separable, what does that mean? What that means is that there is no interaction between the two subsystems. Okay? And so that would say that there is a Hamiltonian that acts separately on subsystem A and on subsystem B.
That's a direct sum.
So this is the sum of two matrices or two operators. Okay? It's a direct sum is a sum between two different subspaces. Okay, so there's all these different sums and products. Okay. If that's true, then the time evolution operator that acts on the joint systems is what? It's a product of unitary. So this would be a unitary that acts on subsystem A and a unitary that acts on subsystem B, right? This would be that, and similarly, we have the time evolution acting on subsystem B, okay? So if my Hamiltonian acts separately on the two subsystems, then the unitary evolution is a product of unitaries on the two subsystems. So separable is equivalent to non-interacting. The two subsystems don't interact. Okay? In that case, we would say the unitary is separable. So separable with respect to the Hamiltonians as the sum of the Hamiltonians, and separable with respect to the unitary is the product of the two unitaries. And what this would say then is that the if I had such a situation, then if we start with this product state, then at a later time, we have a product, okay? So, what this says is that if we have such an interaction, if we have such a Hamiltonian where we have no interaction between the two subsystems, then we can't create entanglement. If we start with a system that's unentangled, it'll remain unentangled, okay? And so, one of the important lessons here is that if we have local interactions, for, let's say, a local Hamiltonian on each subsystem, then we can't create entanglement. Entanglement requires interaction between the subsystems or between the different degrees of freedom. And in general, what one often says is that if we have local evolution and classical communication. So if I can imagine I have the ability to call up the remote party, tell the remote party something about my system, and tell them to do something to their local system, then they can't generate more entanglement. So this is what's often called LOCC in the jargon, local operations and classical communication cannot change entanglement. We need something beyond that. Okay. We need interactions. Yeah.
By change, you can't increase it, right?
That's right. I can also, that's a good point. I can't increase. That's a better way to say it. Thank you, Tristan. Yeah. All right. Now, I want to emphasize, so we're going to have to think about interaction. That's a subtle point here. I want to think a little bit, though, about, entanglement depends on the decomposition into subsystems. So while I can't change the entanglement by locally operating on the 2 degrees of freedom, how much entanglement in the system there is depends on how I divide the system into subsystems, the total system into subsystems, what I mean by the degrees of freedom. So for example, if I have 2 particles, 2 degrees of freedom, say with I can think about two kinds of decompositions. I can think about the total Hilbert space as being decomposed into the Hilbert space associated with the position and momentum of particle A and the position and momentum of particle B. But this Hilbert space can equivalently be decomposed into the Hilbert space associated with the center of mass and relative motion of the two particles. And depending upon what that decomposition is, in one decomposition, the system will be separable, and in another decomposition, it will be entangled, right? So let's just think about an example of that. If I have two particles that have that are separated by a certain, say, distance between them, they have a definite relative position. And so if we think about the EPR state is entangled in position momentum of A and B, but separable in center of mass and relative coordinates, right? Because the system has, in this case, it's a product state. If I thought about its center of mass wave function, the center of mass wave function is definite, and that is separable from its relative coordinate. The two A and B are entangled with one another, but their center of mass is not entangled with the relative motion. Is that clear? So that's a very subtle point, and it's to say that what we mean by entanglement in the system depends on also what the degrees of freedom are and what we're measuring in the end, okay? So here's just an example for you to contemplate a little bit. Let's consider a photon on a beam splitter. So let's say I take a photon and it's incident on a beam splitter. Let's say the photon is in a definite momentum state. Okay? So it's a plane wave mode. And it's incident on this beam splitter. What comes out of this state?
A single photon?
A single photon. And the single photon is going, so let's call this K1. It's going to, there's some possibility it goes through and or it could have this momentum. Okay. Is that an entangled state? No, Andy, I saw him shake his head. Why not?
It's kind of like a mixed state, but they're not, I would call them correlated, quantumly.
Well, I mean, I would say, well, is there any quantum, it's not a mixed state. It's not that if this is a 50-50 beam splitter, this is a pure state. So there's no statistical mixture going on, but is it an entangled state?
What's the two subsystems?
Well, it's a good question. What are the subsystems? Yeah.
If we consider just spatial modes.
Yep.
The two spatial modes, we're not able to say that those two spatial modes are entangled?
Well, okay, so this is a good question. So we might just say, I mean, from the point of view, if we think about this as a single particle, this is a particle degree of freedom. We would say that, you know, I start with a state that is a momentum eigenstate, and this thing becomes, say it's a 50-50 beam splitter. I mean, this is standard quantum mechanics, where we would just say that we have a superposition of different momentum eigenstates. We would call this, typically, in the semi-naive place, this is a superposition state. Okay. So, from the point of view of thinking about the particle degrees of freedom, there's no entanglement, as Arik was saying. What are the different subsystems? There's one system, it's the particle, I can have superpositions, but I don't have entanglement. But if I thought about this in a slightly different way, so this is a particle picture. There are other degrees of freedom that I think about associated with the field, which are the modes. So this initial state, I can think about as there being one photon in mode 1 and no photons in mode 2. That's my input state, right? What's the output state? In this picture, and thinking about it in terms of excitations of modes.
One of the two different permutations.
So either the photon is transmitted, or the photon is reflected, right? Is that an entangled state? Yes. So that's interesting. I can, from the point of view of the particle degrees of freedom, there's no entanglement. But from the point of view of the modes, there is entanglement. Yeah?
Does this change if we aren't using a particle and instead using coherent state?
Well, it's a good question, yeah. So that's an interesting question. I mean, if my state was not a Fock state, but was a coherent state, if my input state was this, then what happens? What's the output state?
Just R alpha and T.
You did this.
Yeah, it's going to be equal to, I'm going to have a situation where I have 1 over root 2 alpha in one mode, and so half of the intensity will go one way and half of the intensity will go the other way. So this state is not entangled. This state is. Whether or not I can generate entanglement depends on the interaction, also on the initial state. Yeah.
Have we defined whether or not entanglement is fundamentally quantum in all cases yet? Have we done that?
Well, what does that even mean?
Is every single entangled state have a negativity in there with it?
The answer is no to that. And you'll see that for homework. This is coming up. Yeah. So the notion of, but it doesn't mean negativity is not the only thing. Even I can have a state, the EPR state is such an example, which has no negativity. So it does not violate those inequalities, but it is a resource for teleportation. Yeah, sure.
The golden state is a superposition of the Fock state.
Correct.
So why can't we think of some photons going into some
Yes,
mode?
indeed. That's a good question. And if you may or may not remember, we studied this last semester having to do with the Poisson statistics. So we have to look at the superposition of all the possible Fock states and the randomness of the photon going through or reflected preserves those Poisson statistics in such a way that there are no correlations. I need sub-Poissonian statistics in order to get those correlations. So, and yeah, so then, you know, continuing with what we were just saying here, this whole story back in the day caused a lot of debate. Should we call this an entangled state? It's just one photon, and you know, isn't entanglement about non-locality? And you know, there's just one photon local with itself. I can't. But it is from the point of view of a resource that we could use, for example, for quantum teleportation or to create other entanglements. Here's an example. Suppose I have this, at the output of this beam splitter, I have two optical cavities in which I have placed a two-level atom, okay, which has a ground state and an excited state. And suppose I prepare the atom in both of these cavities in the ground state, okay? And then I put this single photon on the beam splitter. The photon might enter this cavity, or it might enter that cavity. And suppose I've set it up with the photon being exactly the right pulse duration, that we do a perfect pi pulse in the same way we studied for the James Cummings model, that if I have a single photon, it will oscillate due to the vacuum Rabi oscillations, as it's called, or the one photon oscillations from this, okay? So I start with one photon in mode 1, and I have the atom in the ground state in cavity A, and the atom in the ground state in cavity B. Okay. And now I pass it through this beam splitter, and I do this experiment where the photon goes through, and if the photon enters this cavity, it causes a pi pulse. What is the state after the fact? Well, it's this, and then if the photon, it gets absorbed by one of these atoms or the other. And so afterwards, what I'll have is no photons in either of the modes, and I'll have either it went through the first, if it went through and was transmitted, this guy will go to the excited state, and this guy will stay in the ground state. Or if it went the other way, this guy stayed in the ground state, and this guy went to the excited state. Yeah,
So this is effectively a way to turn the photon entanglement into like an atomic.
for example. So clearly, there was entanglement in the beam splitter, right? The entanglement was arising from the mode entanglement, not the particle entanglement, but it's a resource, because clearly I could not have created this entangled state if there was an entanglement in the field to begin with. Okay. Yeah.
Does it change our view on entanglement? Because the way I thought of like particle states, for example, particle states is something that don't have any entanglement, but now it seems like entanglement is observed.
So I think what's important here is that entanglement is dependent on the division into subsystems and what those subsystems are. So if, as we were saying over here, if my two subsystems are A and B, if those are my degrees of freedom, then a state that's the EPR state is entangled between the position of A and B. But if instead my subsystems are the center of mass motion and the relative motion, then it's separable.
So a way to check if a state has entanglement or not would be to check across across all the different nodes.
That's right. We'd have to think about over all possible divisions into subsystems. And we can't, until we define the tensor product structure, until we've defined what we mean by the subsystems, there's no way to check. We have to look at that division. Okay, so is the beam splitter interaction a separable or entangling interaction? Well, it's got to be entangling in some way because we were able to make this entangled state this way. The beam splitter interaction is one which annihilates a photon in, say, mode 1 and creates a photon in mode 2, right? From this perspective, we see there is an interaction. This is not a separable interaction with respect to the modes. It doesn't mean, as we just saw, that we will, for any state, this kind of interaction will generate entanglement. As we said, if we had the coherent state example over here, we didn't generate entanglement. So just because there are interactions doesn't mean every output state is entangled, but it means there can be states. And in fact, if we look at the unitary transformation on the two modes, let's say for a 50-50 beam splitter with a particular phase between those modes, so this is a 50-50 beam splitter, this is the transformation. So if we thought about the quadratures of this system, so these are the quadratures for mode 1 and mode 2. What is this transformation? Well, this transformation effectively took me from the coordinates of mode 1 and mode 2 to the center of mass and relative coordinates between the two. And we can see how that can, in principle, as we just described, in one case, take a state that's unentangled to an entangled state. We saw that for a single photon case. It didn't do it for the coherent state, but here's another example. Suppose I have the beam splitter, and in each of these modes, I'm going to put a squeeze state. Say squeeze vacuum. So this is a product state, the input state is two squeeze vacua with some squeezing along some quadrature. What comes out of this? So what comes out, this is a two-mode squeeze state, which is a separable squeeze state. What comes out of this, in the end, is an entangled state. Because we've gone from the two quadratures being separable to the two quadratures being entangled, going from the center of mass kind of coordinate to another. This is how I would make a two-mode entangled state between two squeeze states. Of course, I need there to be non-classical light at at the beam splitter, in order to create this entanglement, if I had classical light, be it coherent state or any state with a positive P representation, like thermal state, that would not create entanglement. Okay. So this is kind of interesting. It says that linear optics can create entanglement, but I need to have non-classical light to begin with. Okay? So if we want to think about that, we want to think about sources of non-classical light and the entanglement of them. So to have entanglement, in light, it must have non-positive Glauber P representation. Okay. All right, so we want to talk now about the creation. We've talked a little bit, we talked about the creation of squeeze light through three-way mixing, but we haven't talked about the entanglement associated with the light that is generated from nonlinear optics. That's what we're going to do for the rest of this lecture and tomorrow as well. Okay? So, nonlinear optics. Let's remind ourselves what we talked about. So remember we talked about three-way mixing. We have a Chi2 crystal. And what we have discussed in the past, let's get our fancy chalk here, is that if I have a pump that is at some sufficiently high frequency, and if I put into the system a signal at some frequency, then I will, in general, amplify this through parametric amplification. At the same time, I will generate an additional beam, a phase conjugate beam, which we call the idler. God knows why we call it the idler, but we call it the idler, which is generated in the process, and that we discussed just in terms of classical Maxwell's equations. And the way we saw it is that for this process to happen, for parametric amplification to be efficient, we had to have phase matching. So in phase matching, what we described is that we need to have effectively momentum and energy conservation associated with the photons, but from the point of view of classical electrodynamics, it's just that the phase of the propagating waves have to be in phase with one another. Okay? And so we have a situation where we would have the sum of the wave vectors add up, so that we have K probe is equal to K signal plus K idler. And in addition, we need to have that the sum of the frequencies add up, right? And that was the process of parametric amplification that we saw and we studied before, and we showed how that could create squeezed vacuum, right? Let's think about this now. Suppose that we don't inject a signal into this system at all. So we have our type 2 crystal. And we pump it. What's going to happen? Now, in this problem, we don't have a signal field, so we don't amplify anything. There's no other field. But what happens, actually, is that we get what we call parametric fluorescence, or spontaneous parametric. Yeah.
So is the idler and the source K equal?
No. This guy, they're not equal for two reasons. This guy is propagating in this direction, and this guy, so it's
Or
wait.
the wave number.
The length, no, they're not necessarily necessarily at the same frequency.
Okay, I see.
We could have degenerate parametric down conversion where they have the same frequency and or the same direction of propagation. But in general, in order for us to have phase matching, these are the conditions. Okay? So one possibility is that I get, as we just saw, a beam coming out like this, because that is an example of a phase matched, but it's not the only possibility I could have. I could have a situation where, for example, I have something that looks like that. As long as these two vectors add together and at the same time this adds together, then I can get phase matching. Okay? So another possibility is that I pump this beam and I get degenerate, something that looks like this, okay? Plus dot, dot, dot. And who's to say which one happens? We can't, if we don't know, if there's nothing in the universe that tells us which of these processes happen, then they happen in superposition. And if they happen in superposition, what I have is an entangled state. The entanglement in this case is an entanglement associated with the momenta of those photons, to the degree to which we'll come back and think about the polarization of the photons as well. That's another story in the system. So when I pump this crystal, I'll do my best to sort of draw perspective here, and I pump it in this direction with a pump beam. What comes out of this system is a set of cones that is coming out. It's supposed to be propagating. My ability to draw perspective is limited. But it's all propagating in that same direction because this is rotationally symmetric. So it comes out anywhere along the cone. Any of these things, if I rotate this around this axis, it's azimuthally symmetric, and I can get photons coming out in this rainbow. Yes, Ari?
Why does it have to be a superposition and not like a statistical function?
Well, we'll come back because the Hamiltonian allows for all of these terms in superposition. So we'll write out the Hamiltonian in just a little bit, but in what's happening in the system is that there's a probability amplitude for all of these different processes to happen, and we don't know which one's gonna happen, and thus they act in superposition with one another. Okay. Right. So let's just talk about the phase matching conditions. We have to have that the sum of these guys add up. And if I call this angle the angle between the pump axis and the directions of these guys as such, then what we have is that the K, okay, so the magnitude of K is equal to omega over C times the index of refraction, right? And as you may remember, in order for us to have phase matching, we have to think about the index of refraction. We can't do this if all three waves have the same functional form of the index of refraction. We have to have a different functional form for at least one of the waves in order to be able to satisfy those phase matching conditions. And that is done through the polarization dependence of the index of refraction for the different propagating waves. And the simplest case is what we call type 1 phase matching, where we have one polarization for the pump and the orthogonal polarization for the signal and Idler, and have them be the same. So all of these guys have the same polarization, but it's orthogonal to this guy. But what's key in what's called type 1 phase matching is that I have is that the signal and Idler have the same polarization. When that's the case, we're not going to get polarization entanglement. We only have entanglement in this case that's associated with the momentum and the motion of the individual particles. Okay. Yeah.
How do we accomplish this? Sorry, I might not be.
How do we accomplish this?
Like, why does going in at one polarization result in the other two being vertical polarization?
The answer is because, as well, let's just write it down, that is the thing that satisfies the phase matching condition. So let's just write down what the phase matching conditions are in this case. So this would tell us that let's say that this is we have two different axes of polarization that have different index of refraction. This is, say, the extraordinary direction, and this is the ordinary direction. Say the horizontal direction we'll call the extraordinary direction. This guy, the ordinary. Doesn't matter which one is which. So this would tell us that the pump frequency times its index of refraction is equal to so this is if I break this up in this vector into its component along K and its component perpendicular to K, I get these two equations. So this is the component of K along this direction, the cosine, and this is the transverse component. So the answer to your question, Tristan, is I choose the orientation of the crystal such that this is satisfied. All right? So in this case, the two photons have the same polarization. Okay? So let's think about this. Thus, what happens in order for these things to be satisfied? In order for this to be satisfied, the transverse component of the two wave vectors must be opposite to one another so that they cancel relative to this. Okay? So if I look at this cone straight on, let me get my notes here so I can get this right. Then it comes out as follows. I do it backwards. Oh well. These are the ways that it has to, in order to have things matching. So what this says is the following. Relative to this picture, I want to think about these colors in the opposite direction. If say one of the photons is emitted in this direction, then it must be that its transverse component cancels. That means that there's a conjugate photon which satisfies it like that. Nope, on the green.
Why on the green?
Because the energies have to add up in the right way. Let me redraw this because I think my picture is not quite correct. If I want to have phase matching, then these guys, this guy, say, has a very high frequency, means it has a long guy, and then I have to match that with a short wavelength, which means also, so that's a possible phase matching, so that can add up. This is a long vector and a short vector adds up to this. And the orange ones will say the guys that are degenerate, okay? So the orange guys look like that. And that can all satisfy these two things so that they have, the colors add up and the directions add up. Yes, Tristan?
And then I assume we could also have a short red and then a long green.
Yeah.
And then that would just be like, would they be indistinguishable, I suppose?
Well, there's everything that's on the cone isotropic, which is what this is. Okay, so these are two wave vectors that can satisfy this, or I might have this guy. Maybe it's over here, and then the transverse component that's on the opposite side of the cone is this one. Or I can have what we just said, degenerate case. I could have a guy over here and a guy over here. So these different shapes that I'm drawing represent different pairs of photons that could be emitted in this process and satisfy phase matching condition. Which means the following thing. If I were to put a pinhole at the output of this crystal and only let through this photon, that signal photon, there will be a twin photon, in this case this one, which will be emitted in that direction. Because those are the two directions that are phase matched. Alternatively, if I put the pinhole here, then I will see the emission of a conjugate photon, a twin photon there, etc. Yes, Ben?
So
there any downside to just putting in multiple pinholes so we can have multiple entangled photons?
Well, you're only, in this case, what I'm looking at is two photons. So I have the superposition of this combination, and this combination.
I see.
Only, but I don't know which one it is, which is what makes it entangled in the first place. Yes?
But if I put the two pinholes like Benny said, or some number, if I put two pinholes down, am I now just in an entangled state with the two modes?
Correct.
Okay.
Then I could restrict myself to just those modes.
So if I wanted a Bell state of some sort, I could just, instead of this like continuous superposition of.
Right. Well, we're going to talk about the nature of this entangled state in a little bit more detail. Okay. And to read through how this looks like a Bell state or not. Okay. So with that, let's be a little bit more formal and think about the quantum state from the point of view of how the time evolution generated by the Hamiltonian generates this kind of entangled state. So, my Hamiltonian in this situation, you will remember, is the interaction between the dipole density, which is the polarization density, and the electric field. That's a fundamental Hamiltonian that defines this kind of interaction. And when we had the nonlinearity, that was the chi2 nonlinearity, this thing we said is equal to some chi3, and then we have the three waves. So, I'm sorry, chi2, not chi3. It's chi2, it's a three-way mixing. We have the pump, which could be annihilated. So there's the positive frequency component of the pump. And then we have the annihilation of the signal and the either. And then we have the Hermitian conjugate of those two terms. Now, each of these fields is associated with creation annihilation operators. If we have the non-depleted pump approximation, we treat this as a classical field. And these guys each are associated with the quantum field. So this guy, we integrate over all the possible modes. I'm going to take this as a continuum of modes. We have the square root of h bar omega, that's the vacuum energy. And then we have the creation operator associated with that mode. And I'm going to leave off the polarization label because everything is polarized in the same direction. As such. Okay? And there's a minus sign in this case because it's the conjugate. And so when all is said and done, what I have in this situation here is a whole bunch of constants. Constants that depend on chi2, they depend on the amplitude of the pump, etc., the area of the pump. And then I'm going to have a term that looks like the creation of a photon in that mode associated with the signal mode, the creation operator associated with the either. I have the integral over the crystal of e to the I k dot delta k dot r e to the minus I omega pump minus omega signal plus omega t. Okay. this is an integral over the signal modes and the Eigler modes. Okay? All right. With that said, our time evolution operator, what we're looking at in this case is a scattering process where the pump mode comes from way out and then comes through and scatters into these other modes. So we can think about this as this S matrix or the scattering matrix. It's a time order product going all the way from minus infinity in time to plus infinity. Okay, this is our time evolution operator. Now, we're going to act this now on the initial state of the field. The initial state of the field, in this case, is the vacuum for the signal and active modes, right? So this thing gets acted upon on the vacuum. Now, if this is a weak interaction, that is to say, the spontaneous decay of this photon, this pump photon, into signal and idle photon is a not very efficient process, then I can effectively expand this to first order and write this as 1 minus I h bar times the integral of the interaction Hamiltonian, approximately that, if it's a weak interaction.
By efficient, you just mean you to drive it really, really hard?
No, it means any pump photon that enters a crystal has a low probability of decaying into the signal either. Most of the time it just goes through the crystal. But every once in a while, it can spontaneously decay into a signal and either photon. That's what I mean by efficient. That depends on the strength of chi2. Chi2 is weak, generally. Okay? So, if this is the case, this is equal to the superposition of the vacuum and this, approximately. Okay. So let's take a look at this guy, putting in this Hamiltonian up above. What do we see? What we see is that the state of the system I can write as the vacuum plus an integral over all modes times something I'm going to call psi sub 2, that's a function of these two. I've lumped everything that's not in, everything that's inside this integral into this factor. What does the state look like? This is the vacuum, and this is a two-photon state. The state that arose from the annihilation of one of the pump photons and the creation of a signal photon and an either photon. The amplitude by which that happens, and this comes back to your question, I mean, as you see through here, this is a superposition through this integral of all possible signal and idlers with an amplitude weighted by this psi. We can think about this guy as the two photon momentum state wave function. Is this an entangled state? Well, it depends. Is this a product state or not a product state? If the momentum space wave function is a product state, this thing is non-entangled. But if we look at this integrals and so forth, for perfect phase matching, this two photon wave function is equal to that is to say, any two, oops, this is signal and idler. Any two wave vectors, this wave function for perfect phase matching will be 0 unless these two conditions are satisfied. Unless the sum of the photon frequencies add up and the sum of the wave vectors add up. Okay? Is this an entangled state? Absolutely it is. And in fact, it's an interesting entangled state. This is actually the EPR state. Let's think about that a little bit more carefully. The EPR state, with respect to the position and momentum of the photon along the direction of its propagation. So let's go back and let's look at this problem again and go back to what we're saying. We have this crystal, and let's suppose I have these pinholes, as we suggested, okay? So I'm gonna look, there's of course, when I have this, the pinholes, I wish I had more colors, there's a range, the pinhole's not a point, it has some extent, so there's a spectrum of light within here that is determined by the size of this pinhole. And there's another spectrum of light associated with that pinhole. But I've picked a particular direction in space, okay? Or at least a paraxial set of directions that are associated with this pinhole. If I then do this, if I think about my two photon state, with the right pinholes, that picks out a particular direction, but allows for a particular spectrum of this, then I can write this two photon state in the following way. There'll be some spectral function, I'll call this A as a function, let's call this the signal photon. There's some function here that depends how big that pinhole is in terms of the spread of these guys. But if to the degree to which, okay, let me say a couple more things about this. This guy is then equal to, if I take the Fourier transform of this from frequency to time, then this thing I can write in the following way. Let's examine what this means. Let's look at this state. What this says is that within these pinholes, I create a photon in this pinhole and in its conjugate direction, such that I satisfy the phase matching conditions, but with a range of frequencies. But these two frequencies have to add up to the pump in order for it to be energy conserved, okay? So, equivalently, if I think about the time of arrival of this photon, the photons thus that are coming through these pinholes are wave packets. They're pulses in time, which have a spread in frequency, and they have a certain extent. The duration of the pulse in time is the inverse Fourier transform of the spectrum. The wider the spectrum, the shorter the pulse, okay? So what are coming out of here are not monochromatic photons, they are wave packets. The degree to which that is a pretty broad band of spectra means these are very short wave packets. But their energies add up. On the other hand, if this guy was flat, if I had a perfectly broad spectrum, what does this thing become? This thing becomes a delta function. If this thing has a flat spectrum, right? This kind of state is sometimes called energy time entanglement. Let's think about this for a moment. What this is really saying, I think we should think about the photons as particles. The frequency is related to the magnitude of the momentum, okay? So what this is saying is that the center of mass momentum of the two photons is fixed, but its relative momentum in this case, or the relative, I mean, it's the other way around. The center of mass is fixed, and its relative position is fixed. Let me try to say this again, okay? Remember, we have two particles, and now because they're traveling along some direction, they're traveling like this, okay? What this is saying is that the center of mass is fixed, and it's relative. These guys commute in the same way that we said we can have the center of mass momentum and the relative position is fixed. They commute with one another.
Relative position in time.
Yeah, but time is space. Because if I'm over here and I'm saying, does it arrive here or does it arrive here, it's equivalent to saying they were separated in time relative to the retarded time. They're moving at the speed of light. They're one and the same. So what is the nature of this kind of interaction? What this is a situation is where what we have in this kind of entanglement, the two photons are born at the same time, to the degree to which this is a delta function. But their birthday is completely uncertain. What this is saying is to the degree to which this thing is a plane wave, where the pump photon is completely uncertain, right? So I don't know when the photon is going to be born, but when these two photons are born, they're born effectively at the same time. And that was actually in the Hungel-Mandel experiment what they were testing. What they did is they took the output of these two pinholes over here, and they sent them, reflected them onto a beam splitter, if you remember. And then they looked for coincidence counts. And the degree to which you saw coincidence counts was the degree to which these two photon wave packets overlap with one another. And what they found was that if they moved this beam splitter a little bit so that the way one wave packet was delayed relative to the other, they would not see these coincidences. This gives us a different kind of two-photon interference, and the entanglement that we see in this problem is arising from the degree of freedom that has to do with the position and momentum of the photons. This is not about its polarization. We'll come back to that next time. So I'm going to show you one example of this. And let me just maybe, given the time, and I know that there's an exam coming in here very soon, or at least I think there is. That's why no one's here today. Or they might be here because they just don't feel like coming here, but I think.
Let's assume it's the test.
That's why we would.
Yeah.
Or everyone just hates me. All right, I want to show
Hopefully
you.
we were making these slides for March meeting.
There is that too. I'm going to send a message to everyone. Okay, so while this is coming up, I just wanted let's consider the following kind of interferometer. Here's my Chi2 crystal, and I'm going to set up two unbalanced interferometers. Okay, so I have a pump, photon comes out, and it goes through two interferometers. In one interferometer, I have the signal and the idler photons. I put the pinholes appropriately to take just those two photons, and I send this wave packet through this interferometer, which has a long path, a short path, and a long path for the idler. And similarly, there's a short path here and a long path here, okay? So I want to just, in 2 minutes, think about the following problem. Suppose I have a detector at the output port of this guy, and I look at it as a function of moving the relative length between these two paths. This is not a balanced interferometer. There's a short path and a long path. If my wave packet has a coherence length that is short because it's a narrow band, it's a broadband pulse that's a very, very short pulse with a broad spectrum, then if the pulse went through the short path, it doesn't overlap with going through the long path. This is delayed, and I will see no interference because the relative length of these two arms is long compared to the coherence length of the pulse. And so I won't see any interference if I look at the amount of intensity or the amount of clicks I get on this detector as a function. It'll be flat. And similarly over here. But what if I look at it in coincidence? So I look at what the coincidence count rate is. Then there are two histories that could lead to a coincidence. What are those two histories? One history is that they both go through the short pulse, or they both go through the long pulse. Those two histories can interfere with one another because we don't know when the pair was born. We know they were born at the same time, but we don't know when they were born, so that there is complete coherence with respect to the two-photon interference. Those two histories interfere with one another. So let me just show you this. This was a work done when I was a student in this lab. This was the lab I was a part of as a PhD student. By Ray Chow was our advisor, and Paul Kwiat and E.P. Steinberg, who are now quite famous physicists themselves, did this as graduate students. And the experiment is done here. So this is a KDP, it's a Chi2 crystal, and we have these two pads where we have these individual detectors and the coincidence between them. And what they saw is the following. If you look at this prism position, you look at the amount of counts you get on one of the counters not in coincidence, you see no interference. But if you look at the coincidence counts, you see interference. And the interference happens at a frequency that's associated with the pump photon, not with the signal and idler, because it's a two-photon interference, and those two frequencies have to add together to that total interference. So this is an example of two-photon interference that's coming from, in this case, energy-time entanglement. All right, then, I know you guys gotta get ready for the next class. We'll call it quits and hopeful to see the rest of the class next time. All right, have a good afternoon, everybody.
Yeah,
Yeah.
for what it's worth, I was talking to Stone yesterday.